Hey everybody, I hope you're having a fantastic day. It is beautiful outside. All of the winter snow is gone, and now it's nice, gorgeous spring. And so, wherever you are, whenever you're watching this, I really hope that it's also pretty sunny as well. This is lesson 5.2. We're going to be using limits to find tangents and then also developing something called first principles. There were some concepts in the previous course called advanced functions. That is our MHF for UO course. Some of those concepts would really help you to understand this lesson a little bit better. And so if you need to brush up, go to my MHF for UO playlist and watch the videos on the average rate of change and the instantaneous rate of change. So those videos are going to really help you to understand this one. Okay, so let's get started. I'm going to call this function f at x because they didn't give me an equation. And let's just describe q for a second. So we'll say that q has an x value of x and a y value of taking the x and subbing it into my f at x. It would be f at x because we don't know what f at x is. That means that the coordinate for q looks like this. Right? This is going to be our y because we don't know what the equation is. We can do the exact same thing for p, and so instead of using x, I'm just going to use an a, and then I'm going to plug it into the function and get my y value, which is f at a. Now the coordinate for p would then be a, f at a. I'm going to move that aside because we don't really need that yet. In advanced functions, we also learned about a couple different terms, and so one of the terms was a secant. And a secant is a line that basically goes through my function more than once. Notice that the black line goes through the blue function at 2 points, p and q. So this is a secant. Whereas if I just move the secant a little bit, it can skim just the side and touch at only 1 point, which is point p. And that's basically what limits is. You're just going from a secant to a tangent instead. Now I'll show you a little bit more, but I'm just going to shorten my secant. So that's a secant right now. Know that it goes on forever, but I wanted to show you I can make a right angle triangle out of it. And if I asked you for the slope of PQ, you could easily figure it out. I mean, it's just the rise over the run. Like your rise would be y2 minus y1, and your run would be your x2 minus your x1. Right? So let's write that on the side. We're going to go y2 minus y1, x2 minus x1. That's just a general slope formula. But if I were to tell you that q can move, pretend that q is moving along the function closer and closer to p. Well, that means that your secant is also moving closer and closer, and its slope changes each time. So eventually its slope is just going to be the tangent, and that happens when your q reaches p. What's happening is this gap that's between p and q is slowly closing, and so x is approaching a. And that's what we write as a limit. We go limit as x approaches a for your secant is going to become a tangent. Okay, now depending on where p is, because if p was here, then we get a different tangent altogether. All right, and that's basically what this video is going to be about, finding many, many tangents. Okay, video done. I'm good, right? No, you're going to be like, okay, let's do some examples now. That would have been great. It would have been like the shortest video ever. Okay, so example number 1. Find the slope of a tangent to the curve, and they've given you an equation at a specific point. And so this is going to be my formula, and I think I might want to draw that just to kind of get to know it a little bit better. So I'm going to factor out an x, and that means that I have my x-intercept at 0 and at -3. Okay, so something maybe like this, and it looks like it's opening up. Something like that. Okay, sort of. This is going to be my p, and that's going to be at x is 2. And so right there, that's where p is. What they're basically asking you to find is the tangent, so a line that just skims through P. What is the slope of that? It looks like it's a positive slope, so we should expect a positive answer. But basically, we're going to use our formula, okay? And I think I might want to know what all of P is. So let's just get into that. I'm going to take 2, x is 2, and I'm going to sub it into that formula. Okay, so that I can get a y value. Okay, that means for p, when x is 2, y is 10. If you take a look at that previous diagram that we just went over, you just found your a and your f at a. Remember, that was what p was. Okay, your q was your x and your f at x. Okay, so this guy is f at x, right? Let's take all of that information, a, f at a, x, f at x, and put it into the equation, because the equation was I have a slope, and that was the limit as x approaches a for my f at x minus f at a over x minus a. Okay, so let's just follow that a little bit. All right, so limit as x approaches, well, a is 2, right? So we'll just put 2 right there. F at x is x squared plus 3x. That is squared. Minus f at a was 10. All over x, that didn't change, minus our a, which was 2. Okay, so we're not really done. We got to solve that. And last time in our previous video, we were like, okay, why don't we just take the 2 and start subbing it in everywhere we see an x? Well, we're going to have a problem. Your denominator is going to be a 0. So we can't sub it in right away. That's why we had learned we might want to simplify it after we factor it. Let's try to factor it then. So I'm going to clean up the top and take out that bracket and see if things look a little bit nicer to me. Okay, the top is probably factorable. And I'm really hoping that if I factor it, it'll cancel out with something on the bottom. Okay, so x minus 2 and x plus 5. All right, that's perfect because it cancels out with the denominator, because that was the problem part. Now I can sub in 2 and it doesn't even matter. So I have limit as x approaches 2, and the only part of the function that's left is x plus 5. Okay, so I can take this guy, put it right in there, and then I'll be 2 plus 5. That means the slope is 7. What you just found is this guy. The slope at this particular part is 7. And if p were somewhere over here, it wouldn't have been 7. It would have been something else. Or if p was over here, also something else. Notice that, like, depending on where p is, there's infinite number of slopes. Okay, and that's why they always have to signify, okay, p is at x equals 2, so that you only have one answer instead of like a whole bunch of them. We're going to write it therefore, the slope of the tangent at x equals to 2 is 7. Okay, let's try something else. Example number 2. Pretty much the same thing. They gave us a function, looks like a square root function, that was stretched by 10 and moved up 1,000. Let's just move that. Okay, so let's say this is 1,000, and that's our square root function, right? They told us specifically which tangent they want us to look at. They want us to look at it where p is 100. And so let's just say that 100 is right here, and if I go up, this guy right here is going to be my p. I want to find the slope of the tangent that just skims p. So what is this slope? What is the slope of the red line? We had just gone over finding out what the y value is first, because we want to know what p is. I took 100 and I put it into the blue function, and so I get my a value and my f at a for my p coordinate. All right, now your x is just going to be x, and this is going to be your f at x. Okay, so we're going to plug that all into the formula for the slope of the tangent. All right, and we get something like this. Okay, and simplifying it a little bit gets us right over here without the brackets. Now it's getting a little bit more difficult. If I sub in the 100 right away from the limit, unfortunately, we're going to get a 0 in the denominator, so we can't do that. I think the root was really bothering me, and so I think I might just multiply it by the conjugate, which is the opposite of this negative, but make sure that you put it over itself so that the entire thing equals to 1. That's how this guy got into the denominator, so it's actually right there. The numerator combined with this guy was a difference of squares, and so that nicely got rid of that square root. Okay, now I don't have a problem anymore. Okay, so I can sub in the 100 right now with whatever's left over, and what is left over is that 10 over the root x plus 10. So that's the function, that's the function that's left over that I'm then going to sub in the 100 right into my x. And so I get a slope of 1/2. If I go back up to my diagram, you'll notice that, yeah, the slope of that red tangent looks like it's growing very slowly at probably 1/2. Now that we kind of get it, let's build on first principles. And so first principles is basically the same thing. I have my a and my f at a for p. Okay, so that's going to be a, f at a. The only difference is now I'm going to just say that a is going to move over a certain distance, and we'll just call that distance h. And so we'll call this x value a plus h. That means that if I sub it into my f at x, I'm going to get f at a plus h. Okay, so that's my q. It's going to be a plus h for my x value and f at a plus h for my y value. Now, q is still going to get closer and closer and closer towards p, and as that happens, you'll notice that h is going to go towards 0. Okay, like that gap between it, h represents that gap. As h goes towards 0, that means that we're going to get a tangent instead of a secant. Now, I don't remember what I wrote down for that. Blank, and so, I forgot. Duh, okay, a's cancel out, and so we have f at a plus h minus f at a all over h by its lonesome. It's basically the same formula that we had before, but instead of f at x and your x, we then just replaced it with the a plus h. Okay, so this guy right here is what's written underneath, and that is our major rule, which is called first principles formula. So let's see it in play. Okay, example number 3. We have a formula, we have an x value, but we're going to use first principles. So on the side, what I'm going to do is I'm just going to make sure that I have my p. Okay, so this is our p value, yeah? And then we also have our formula, and we're trying to find that slope of the tangent. Okay, so I'm just going to put everything into that equation, limit of h approaching 0. So we're going to change that to h approaches 0 now. There's no more x's, okay, because our formula doesn't have any x's in it. It just has h's and a's. Okay, so let's figure out what to put in it, and you're going to have to keep writing the limit as h approaches 0 until you can sub 0 into an h. And you can't do it right now because there's an h in the denominator. Okay, so basically what that means is since this guy right here, remember this is your a and f at a, this is my a value, right? Okay, so what we want to find is maybe, I think we should probably find our f at a plus h. So let's find our f at -2 plus h. We'll plug it into, so plug this into wherever you see an x. Okay, so right here, x is going to be scratched out, and you're going to get -2 plus h instead. Okay, and then instead of the 3x, you're going to get 3, and you're going to multiply -2 plus h. And then you're going to get plus 4. All right, that's what we mean by f at -2 plus h for our first part. We're going to subtract f at -2, and that's all going to be over h. Okay, so let's take a look at this and see what happens. Equals to limit h approaches 0. I'm going to rewrite this entire thing right over here. 3, -2 plus h plus 4. Okay, we're going to subtract. What is f at -2? Well, I'm going to probably have to take -2 and put it into my x's and actually figure out what f at -2 equals to. And then I think when I did that, I actually got something that looks like this. So -2 plus 3 times the -2 plus 4. Okay, and again, all of that is over h. Keep simplifying. That h on the bottom is going to disappear eventually. And so if I keep simplifying, I will get something that looks like this. H squared. Obviously, I simplified a lot. Through the magic of television, minus h plus 2 for the blue, minus 2 for the green, all over h. Notice that these guys will cancel out. I'll have h squared minus h on the top and h on the bottom, and that means that I can divide an h from the bottom with each of the h's on the top, and I'm left with h approaches 0, 1h over here minus 1 over there. Now that the bottom is gone, I can sub in my 0. Okay, so that's going to go right in there. Sorry if I'm going kind of fast. I just figure you guys have these skills already. Oh, I'm subbing in. I don't have to write this anymore. 0 minus 1, which is -1. And so the tangent, that's a lot of therefore statements. Go away. Therefore, the slope of the tangent at x equals -2 is -1. All right, couple more examples. Let's just show you this time. This one's asking you for something different. So instead of asking you for the slope, they're actually asking you for the equation. And you know that the equation of a line should look like this. That tangent is a line. Our answer should look like this. What we've always been finding is just the slope. And so let's take a look and see what happens. We have our function, and we have our p-value. Okay, so this is going to be our a, this is going to be our f at a, and we're going to sub that into our formula for the slope. And so this time we're going to go a plus h, take a plus h and sub it into the blue wherever you see an x. So you'll see that down below, minus f at 2, and you're going to take the 2 and sub it into the x wherever you see the x in the blue function, all divided by h. I didn't like to write like the fraction, and so I just divided it by h like that. I hope that's okay. simplifying that blue, the two blue fractions, and trying to put them together eventually will look something like this. All right, I need the same denominator, right? So I might want to use h plus 1, which just means I have to multiply the top and bottom by h plus 1, h plus 1. So I get something like this. Now I can subtract and then simplify. Okay, so you'll notice as you go down, this is going to be over 1, and so I flip it upside down and it becomes a multiply. And finally, I get rid of the problem. Okay, so those h's are what was holding me back. I couldn't sub in that 0 right away. Now that I've gotten rid of them, I have a nice formula that I can sub in that 0. So subbing in that 0 right here would then give me a final answer of my slope, which is -1. Now that's not really what they asked for, because they asked for an equation. That means that we can take the slope and put it into our y equals mx plus b, right where the m is. Take the point. This will be our x and our y. We can use that to find our y-intercept and finally write the final answer of our equation of our tangent. So here is the very last example. Find the slope of the tangent to the curve, and they give you a root. Now they want to do it at many different coordinates, p, maybe even, I don't know, an r, maybe at an s point. So they're asking you for several different things. What you're essentially doing is you're going, okay, so we have a root graph, and wherever p is, what is the slope of that tangent? Oh, that's kind of off. Okay, what about at r? What is that slope of that tangent? And what about at s? And so creating an overall formula for all the infinite number of slopes, we should do that first. And so instead of using numbers for p, why don't you just use f at a and f at a plus h? Okay, so just using a and a plus h and subbing them into wherever you see an x in our blue function, you get something like this. Simplifying that a little bit by multiplying by the conjugate, I would then get something like this. All right, I'm going to move down a little bit. Then what's going to happen is, notice that you have your a's cancel out and you have an h on the top and an h on the bottom. Those guys are going to cancel out as well, leaving you with a 1 on the top. And then these two, let's see, we can probably sub in our 0 right away, and you're going to get 2 root a's on the bottom. So this formula is actually a formula that describes every single slope of the tangent along your curve, no matter if they're negative slopes or positive slopes or 0 slopes. Now it makes it very easy that if you're asking for a specific point, all I have to do is sub in my a value and then get that slope at that particular a value. So at a is 4, I'm going to sub it into my slope formula. At a is 9, I'm going to sub it into my slope formula. And so at each and every different a value, which quote unquote are our x values, we're going to get a different slope because it refers to a different tangent. This builds towards something called a derivative. And so a derivative is what we're going to see in the next unit. Hope you guys have a great day. Go and enjoy the sun.